And how do I get it? All right. Cool. So hello everyone, and I asked that question because I'll be talking a bit about that as well. So let me introduce myself. I'm Siddharth Chaini. I'm a PhD student at the University of Delaware, and today I'll be talking about how we are sort of tackling LSST's sparse multiband light curves with something called neural processes. And a special thanks to our collaborators, Angelica and Dragona, for here, yay, as well as my advisor, Federica Bianco, who's unfortunately not here, but she's definitely playing a big role. So, Ruben, it's here. LSST will be here with us really soon. And it will be a discovery machine, as we saw in the slides about the TP, like the data, not the data preview, but the first look event. But essentially, it will generate millions of light curves of QSOs, supernovae, TDEs, and so on. And the big promise is that LSST, because it's covering such a wide range of wavelengths, so from near infrared to near UV, it can really advance a lot of previous science. So including search for knowns as well as unknowns. But with the data volume we're dealing with, machine learning is going to be crucial. And that's something we've saw in the previous talk as well. And if you don't do a lot of machine learning, let me take a step back and just tell you briefly about how you would use machine learning for science in TVS broadly. So the first step consists of representing your data. So something like feature extraction. So if you have a light curve like this one here, you can fit known parametric models to it to get numbers that represent those light curves. And you can use those for your machine learning. Other techniques include the use of deep learning for representation learning, etc. And then once you have those data representations, you then use machine learning to do your science. That science could be anything like classification, characterization, or redshift estimation, or systematic searches for a failure transient, population studies, anomaly detection. Everything's fair game, and it all depends on what you want to do for your science. But a big challenge is the sparsity of these light curves. And I'm sharing this screen grab of Alex Razim's slides from last year, and she put it perfectly where some of the biggest problems are that they are a source of unyielding pain because the light curves are variable sizes of data vectors, unevenly sampled. It's difficult to account for uncertainties, and good interpolations are computationally expensive, like Gaussian processes. And I'm also going to steal this visualization, which Alex used, was that if our galaxy images were like light curves, that is, if they were sparse and gappy, they would look something like this. So this is something we have to deal with. This is how we have to do science, and that's just a fact. So the beautiful light curve of this type 1A supernova I showed you earlier, this is in 4 passbands, LSST you'll see in 6, but I'll stick to these for now. But something like this with LSST will look like this. So this is just one realization based on LSST options version 5, the latest one. And this is a typical baseline survey observation of a supernova. So how do we do science with light curves like these? That is a big challenge. And now if we do those same parametric model fits, a lot of them fail because we don't have enough data points. So if you have a model with 5 parameters, you at least need 5 data points. But even the ones that work often give unphysical results. And additionally, another big problem is that most machine learning methods are not really designed for sparse, irregular, or gappy data. So that doesn't really stop us from trying though. And there have been a lot of attempts and approaches with a lot of innovative ways. So people have used multi-layer perceptrons, convolutional neural nets, recurrent neural nets, often with some innovative tricks like masking or padding or other tricks. But the fact of the matter is that these neural nets are not really designed for sparse gappy data. Recently, there has been the use of attention and transformers, which has seen a lot more success when dealing with CAPI data. But at the end of the day, that means you have to use that model, and then you can't use a different. Suppose you wanted to use a gradient boosted tree. You can't use that if you're using a transformer. You can't do a salt fit if you're using a transformer, and so on. So instead, what another method consists, or another approach is we can interpolate our light curves before we do any of the other two steps. So this interpolation, as long as it's good, that can improve all downstream tasks below. So that will improve our data representations, that will improve the machine learning we're doing, and then essentially the science as well. And so the most popular approach here consists of using Gaussian processes as interpolators. And this became really popular after the plastic challenge where Kyle Boone used a Gaussian process as well. And you can see that you can use a GP to interpolate in time. So if you have a light curve that's CAPI on the left there, you can interpolate over time to get a value for each of your time values. But you can also interpolate over wavelength because we know the characteristic wavelength of each LSST filter. We can interpolate both in time and wavelength, and that gives us these images, these heat maps, which we can do machine learning with as well. But Gaussian processes need you to choose a kernel function to model covariance. So I didn't really talk about how Gaussian processes work, but essentially it requires you to choose this kernel function where the kernel function choice imposes a certain modeling between, so it imposes certain covariance between the different features you're modeling. So that in case of light curves, that would be a relationship between the time scales and the wavelength compared to the flux. And so now, if you have a good physical understanding of your the object you're dealing with, you can really do a good job, and you can really choose a very well physics-driven kernel because you know the way the physics dictates your changes in brightness, changes in time, changes in color. But in astronomy, most of the times we don't have this perfect knowledge of the objects we're dealing with. And so we often resort to using kernels that we fit to our light curves. So a common choice here is the Matern 3x2 kernel, where we can essentially, that models the behavior across time. And you can see that in this animation here. But even then, no single kernel will work for everything because we know that the characteristic timescales of different transients, different objects are going to be different. So we cannot use the same kernel, at least not from a physical motivated point of view. And so neural processes try to combat this, try to tackle this. And so neural processes are a family of models that learn distributions over functions, just like GPs, with the help of neural networks. And so essentially what this does is that it sort of combines the best parts of both the neural network approach as well as the Gaussian process approach. Like neural nets, they're very quick, flexible, and data-driven, which makes them really, really good at learning patterns in the data. Like GPs, they produce distributions over functions, crucially giving us uncertainties, which are really valuable and important if you're an astronomer. And so you can think of a neural process like a GP, where you're learning the kernel with the neural network. And because this is data-driven like a neural net, we can use it without spectroscopic labels. So the same model can learn from all light curves. And so neural processes have been used in astronomy before, and mostly in quasar and agent modeling. And we have some experts in this room like Angelica Dragoner, as well as Aman. But my approach is a bit different. My proposal here is that we can use neural processes as a better pre-processing step for all LSST light curves. So I'm focusing mostly on transients here and mostly supernova-like transients, but the methods I'm showing here should work for any light curve. And so let me tell you a bit about how these work. So suppose I have this gappy light curve from earlier. I can take my x and y's, so my dates and my fluxes, and feed them into a neural network encoder. The encoder then encodes each of these observation points into a representation, which is then aggregated into a single representation. And then once you want predictions, you take a decoder, which is also a different neural net, that takes in the representation as well as the new X value where you want to make a prediction. So in this case, that would be dates where we don't have any observed light curve points. And then the decoder generates a distribution which can be parameterized by this mean and the variance describing the y value. So in this case, that would be the flux. And so this central part in the middle, that's the neural process. What I described here is the very basic version of it, which is essentially a conditional neural process. But there have been more sophisticated versions of it called latent neural processes and attentive neural processes, where attentive neural processes use attention, which is the key key driver behind large language models as well, like ChatGPT, for example. And so how do we train this model with light curves? So it consists of taking a perfect cadence light curve, downsampling it to something like we'll see with LSST, and then use that as the input to generate the full complete light curve. And we do this for a lot of different objects for a lot of different classes. And so in this example here, in this talk here, I'm showing you a data set consisting of SNANA simulated examples, where the simulations themselves are based on plastic, and thanks to the Respect team as well as Emily. So because this is a proof of concept, I'm taking a training set in these 10 classes and a test set, which is just one object each, because I want to see how my model works on each object. Note that there is a heavy imbalance in the training classes here, and I will talk a bit about that in a plot later. But essentially, that's the summary. So you take the models, train it on multiband, dense cadence light curves. This training ensures that the model learns covariance in time and wavelength. And we do this for 10 classes, so it learns relationships for these 10 different classes. So let me show you some plots about of the neural processes. So how well does the ANP, the attentive neural process, do on an entirely unseen light curve? So this is a light curve of a 1AX supernova. And the dotted lines in the background, though they are representing the ground truth, while the solid points, the large circles, are essentially what LSST will see. And let's assume that we are in LSST, like LSST is live and we're seeing these points get collected one by one. And so the ANP is looking at these points. And as soon as it sees a rise, it makes a prediction. And you can see that just even though we've only seen a rise in one filter, the ANP has learned that that filter influences the other filters. And that is something it has learned from the training set. And then as we keep going forward, the prediction gets better. And by the end, we have something that looks like this. So this animation is the same thing on the right. That's the attentive neural process. But let's compare it to a Gaussian process, which is on the left here. And you can see that the Gaussian process has much larger uncertainties later on. But it also doesn't do that well on the green band, especially near the peak. That's more like a sine wave. So let's look at another example, a different object, a type 1A supernova. And here you can see that the GP does not do a good job at reconstructing any other filter except the R filter. And so because it's learning the parameters from the light curve, but there is no data to be learned from. There are no other points in the filters except the R during the peak. But the ANP, because it has been trained on this diverse set, it has learned these values. And then the ANP does a much better job at giving fit parameters that are also closer to the theoretical values. But crucially, the neural process it works on all different classes. So the same model can predict the light curves for all the different classes I trained it on. And that works really well if I have 28 points in this example. But it also works reasonably well for most classes if I have 8 observed points. But the classes it doesn't work that well on are classes which it did not see a lot of during training. And finally, I want to end with this point, which is that new filter observation can be really crucial. So this is the prediction if I had the context points on the left here, the observed points on the left here. But if I just add a single point from the green filter, from the G filter here, you can see that the prediction is now much closer to the true values. And so just observing one extra point in a new filter improves the prediction dramatically. This can so follow-up can be really crucial here. But that is my summary, and my code is open source. And I do think neural processes may be the answer to this interpolation process. Training it requires careful selection of the data. But if you think if any of this is of use to you, let's talk. And I'll take any questions. Thank you.
We have time to go to the short questions.
Hello. So if I understood correctly, you like in practical terms, you can only train a neural process with simulations because you need like this very perfect.
Yeah.
So how can you so you have this model and then you try to apply real data and maybe you see that the model is not performing well. How do you make better the model if you cannot use the real data?
Right. So I'm still testing that. So in terms of requiring simulations only, I don't think that's true. But there's not a lot of samples where we have a lot of dense light curves. That is something I'm playing with. But I do think there is a way to use light curves which are not dense, but still better than like maybe using DDF light curves and use that to improve the predictions here. And I think that is definitely something which should be possible. But again, I'm still playing with that, and I'll let you know once I have updates.
Yeah, thanks. This looks really great. But just so I understand, if we get a new sparse transient and we don't know what it is, then we're still in trouble, right? Because we don't know which model to use for interpolation.
Yes. So crucially, it's the same model. That's if it's an entirely new class, it would be something it has not seen before. But it is the same model that we'll use. And then once we're using the model will essentially be very wrong. And that will sort of a higher error rate essentially, or you can use a latent representation there. And that can tell you a bit about that could be an anomaly. So I think there is an option for that approach as well, but obviously it needs testing. So I can't guarantee that, but I think that might be possible.
Very quick question.
Very good. I mean, there will be a lot of questions later. A quick question. Is there any kind of confidence output of the algorithm? Like if the light is completely unsimilar to everything was trained with, will it tell you something? Like, I'm not sure that I have seen this in training sample.
That is something, again, I haven't played with yet, but that'll be a test I will be done. But I think you can design an output value which can tell you about similarity, but I think Angel has some point as well.
Okay.
Thank you so much, Steve, for wonderful work, and it is amazing and heavy lifting to apply to completely other writers. Related to application to the real observed data, completely unseen. We, as a team, it was enough that you, for example, train the data or train the model on the data that you know how it looks like, for example, TV or whatever. And then we run the model on 5, for example, gigabytes of the data. So the advantage of the neural process that it learns the information. And as Steve explained, you can run that model on all data, and whatever it can explain statistically, that is on the larger level of the. And we have been successful to detect about, for example, 300 examples of some types of the gamma flares in gamma light curves, while the human expert detected only about 100. So that was the real-time experiment.
Thank you. Thank you very much again. We're ready to move on. We are going back to TDEs.